I'm Ola Wiberg. I'm a co-founder and currently the VP of Engineering at Human API. So today I'm going to talk to you about unlocking our health data and how to transform or work with that data at scale. So I'll probably focus a little bit more on the scale part rather than transformation, because I'm a data engineer, not a scientist, and not a mathematician. So this will be a little bit more focus on architecture and system design, and compared to probably some other talks you go to during this couple of days. So, Human API. We started about 2 years ago. We launched the first product in the summer of 2013. We're based out of Redwood City here in California. So what we're doing, we're building basically a unified health data platform to enable the next generation of health applications, basically by making it really simple for developers to integrate health data, just working with one API. So, what problems are we solving? So health data today exists both in old and new systems. There is a lot of health data systems out there, hospitals, like legacy systems. So there are a number of difficulties working with that data. Just accessing that data, for example, is pretty hard. Then there are a lot of new systems that are built for health tracking devices, for example. These systems are a little bit easier to deal with, but there's not really any standard across these systems. So we're making it easy for developers to work with these kind of data, basically just working with one API. So some of the challenges with these old and the new systems. So like I briefly mentioned, old systems are hospitals, labs, clinics, Medicare, so it's a lot of unstructured data or semi-structured data. And usually it's a lot of data for specific points in time. So you go to a doctor, they take a lot of tests, there are procedures, so they collect a lot of data about you for one point in time. And there are also a lot of standards, probably too many standards over the years, so it's basically the same as working with no standards in some ways. It's too complicated. New systems, so today a lot of people carry Fitbits, Jawbones. Apple Watch is coming out, what is it, this weekend? Or it will come out in just a couple of days. Wellness FX, you can go to the lab, have your blood test taken, and you can have the results sent to you without involving a doctor. So those are type of newer systems. So the data that comes out from these systems are generally better structured, but everyone has their own structure. It's not a standard here as well. Another thing that's common between new systems is often a stream of data. It's like you have data coming or generated throughout the whole day. So it's not just these points in time. It fills in throughout the whole day. And as I mentioned, no standards. And just to briefly touch on the type of standards in health IT. So there are a lot of terminology standards, so code sets, for example. So LOINC is a code set that determines how to name test results, or it's a standard across test results. And ICD-10 is a World Health Organization classification system just for medical conditions, for example. And nomenclatures like SNOMED for medical namings. And then there are information exchange standards as well. HL7 is the most common. So there are many different versions of HL7. So it can be serial communication, XML, or the latest one is called FHIR, F-H-I-R. So it's for fast healthcare integration resources. So that's a promising standard, XML and JSON. Basically, it's going to be easier to work with systems if they implement those kind of standards. But we have to deal with a lot of different types of data coming in and classifying it based on different standards. So what type of data? when I talk about old and new, I basically say the oldest systems that have been around for a long time. So it's clinical data, medical records, vitals recorded by nurse, and this data usually comes or could come at XML over HTTPS or TCP. I mentioned before, it's deep data for specific points in time. Modern data is personal health tracking, so it's a lot of things that you do on your own. Like you track your data at home, you track your fitness, you track vital signs by having devices at your home, your weight, your blood pressure, blood glucose. A lot of this data is available like JSON over RESTful APIs. So it's not only problems with dealing with this data, it's a lot of valuable data. So both in old and new systems, they're really useful once we can make computers actually understand and work with this data. So, and the new data is filling a lot of gaps from the old legacy data, because it fills in this full picture of a person's health profile over time, not just specific points in time. So we're building a system that enables deep learning from these disparate data sources. So how do we do it? So as you can understand, we have a lot of different data sources coming in, both push and pull sources. It's many different types that I mentioned. We want to process this data in near real time. So basically, when the data comes into our system, we want to be able to process it as fast as possible. Many times it can take a long time before we get the data, but once we have it, we want to be able to process it in near real time. And we also want a lot of flexibility and speed of development. So developer data scientists can work on testing things, working on things without interrupting the flow of production environments. So we're building an infrastructure basically with microservices. We containerize them using Docker. And we deploy these services using Mesos and Marathon. And we have a data backbone where we push all the data through, which is based on Kafka. And we use Spark to work with the data. So I'll go through some of these things in more detail as we go through the presentation here. So the foundation for the data infrastructure is Mesos and Marathon. I don't know if you're familiar with these technologies, but it basically is an abstraction layer on top of hardware. So it's like a cloud operating system pretty much. So we have a lot of AWS servers that we pull together, and Mesos manages those resources for us. So basically how that is done is we install Mesos master, we have Zookeeper to manage it or manage configuration, and then we fire up a lot of Mesos slaves, and Mesos slaves are the ones that actually run the services. And then we use Marathon to manage the services. So if you need to start up and scale up a service, Marathon triggers a job and starts the service on a slave that has resources available. And when it's started, we scale the system, and it's usually just a few seconds. And so if you need to add resources, it's really easy with this technology. And the foundation of the data pipeline is Kafka. So basically we have a Kafka cluster, we have Dockerized apps, and we have producers and consumers for the Kafka topics. So basically the apps are listening for data, incoming data, or collecting incoming data, push it into Kafka, and we have different types of consumers working with that data, whatever it may be. And we also have replay capabilities, so if you need to reparse the data or work on it, we can easily trigger just replay based on Kafka because it persists the data there a period of time that is configurable. But this makes it really flexible to work with the data. So looking at the data pipeline in a little bit more detail, so basically we ingest data, XML, HTML, PDF, or whatever format it is, basically go through. This is a very simplified view of the data pipeline. We do some simple organization, cleanups and extractions, so basic NLP stuff. We do normalization, and then at the end we have a structured data API. So for this demonstration, we're going to look a little bit more detail on data normalization specifically. So as an example of what we need to do is using classifiers to normalize test results. So test results can be blood tests, urine tests, whatever tests are done from the doctor. These tests are often, they can be typed by hand, the name, or it can be used different kind of those systems that I mentioned earlier, or different standards. When the data comes from many different systems, it's hard to know how the tests map and what the correct naming should be. So we're predicting the class, basically identifying the correct name. We're standardizing on units and normalizing values across the different tests. And we accomplish most of this by using Apache Spark. So why Spark? So Spark provides a complete tool set and makes it really easy to work with large data sets across clusters. It has a great stack for doing stream processing, which fits well into our Kafka pipeline. And it also has a lot of built-in tools to do machine learning. And it deploys easily on Mesos, which we are using for our base infrastructure. And it's really fast compared to a lot of other tools that are available, because it can do, it uses RDDs, resilient distributed data sets across clusters. And it also has native Scala Python interactions, and it has a shell. So you can actually work with the data just in command line, which is really nice and developer friendly. So some basics of Spark. It works well in the Mesos setup. So you can actually start up workers, like I showed earlier, where you had Marathon starting services. You can have services or Spark workers started up like that as well, as you need to process the data or transform the data. So you basically have a driver that launches the RDDs and keeps a Spark context. And then the workers are actually the ones that are working on the data, so they can read the data from the stream, from file system, load it into memory, and do transformations on it, like filter maps and unions. And then the driver can call some actions on the workers to collect results, do counts, and broadcast data as well to those workers. So Spark also has, Spark also has a machine learning library, which is more of a framework than a library, because it provides basically everything you need to do machine learning at scale. It leverages RDDs to actually work with the data across multiple workers. So it's really fast if you need to test things on large data sets. It also includes common algorithms that are specifically optimized for parallel environments. So for classification and regression specifically, they have libraries for binary classification, multi-class classification, and regression analysis. And I'm going to demo some code here where we actually use a specific logistic regression with FGS algorithm. So let's look at some code. I know, does a lot of you work with Spark already? So quite a few people. So I'm just going to show you a real simple example here of Spark. So this is Spark using Scala, not Python. So can you see this? Okay, so basically, if you're familiar with Scala, case class just shows you what a clinical test is. So it's basically a test name, label name, and a label value. We have a test result normalizer class, which basically does everything I'm going to demo here. Here's a simple mapping. It's just 21 values for some the test results we want to normalize. So of course the real number of results are in thousands, but for this sake of this demonstration it's just 21. So it's glucose test, hemoglobin level, hemoglobin, A1C as examples. So the way Spark works is you start up or instantiate a Spark context. Basically just take some configuration, give it a name, and create a Spark context. And here I wrap that context in a SQL context, which basically give you, for this demonstration, it's mainly done just to be able to load a JSON file really easy. So I can load JSON data from a file and just perform some simple functions on it. So in this case, I'm loading the training set. So we have a training set here as well as just very few, a small sample here with 90 lines of tests, basically mapping various test names to a normalized test name. So this is generated basically manually at this point because it's just a small set here. So we load that into a data frame. A data frame is a class where you can basically just gives you some convenience methods around working with that data as well. So you can load the JSON data into a data frame and then map across it to generate the actual clinical test. So the clinical test from the training sets, we take those and we create like a term frequency hash based on that. So Spark comes with algorithms for that as well, so you just instantiate that. Actually here I instantiate the class, and then I do the transformation here with the test names, and I return the vector and label values. And so I map over it again, in this case just to generate the label points. And I cache that training data in memory. And then I can use this algorithm to actually classify the data or create a model. So I instantiate that. I tell it, here it's hard-coded a number of classes. As I showed earlier, there are 21 classes for this demo. I take that and I run this algorithm on the training data and generate a model. So that's all I need to do to have a model to work with. I can then save that model. In this case, it's commented out, but you can save that model and then reuse it. So here we're just going to run run through. But you can actually save this model, use it for streaming purpose or for other purposes at a later point, or as in this case, you just use it to do the predictions. So the prediction is done on the model, so you just call predict. And here, at the last stage, you actually do the pass in the values from this array. So we take all these values, we're gonna classify them and see if it works. So I think the resolution is a little bit off here. Just a second. Can you see that? So first, let's just build it. And then to run it, we'll run this command. So basically, when you run a Spark program, you submit it to the cluster, basically. So using Spark submit, and then you tell where the master is. In this case, it's on localhost, and I tell it to use all or 4 cores on the system. So you just send that command, and it's going to run the program. And basically here's the prediction results. So WBC is classified as white blood cell count. White blood count is white blood cell count. So it's working. So that pretty much demonstrates how simple a Spark program you can actually create to do some simple machine learning work. And it's a lot of algorithms available, and you can also use. You don't have to use the algorithms, of course, that are part of Spark. You can use other libraries and plug them in and run them on the workers. So, but it has a lot of things already built in that makes it really simple to get started. So another thing, I mentioned it before that we use Spark streaming. So once you have built this model or trained a model, you can plug it into a streaming context and actually use that model on real-time data as it's passing through. So Spark streaming, it extends the core API. It can ingest data from Kafka that we are using, or other things like just TCP or CRMQ. And it can publish it directly to dashboards or store it to the database, whatever you like. And it's really simple. Here's just a quick example of how you would set that up. So you basically create a streaming context and use the util, in this case the Kafka util, to create a stream. And once you have a stream created, you can just read the data from the stream. So in here, Kafka stream.map, we get the name, and then you can load the existing model. So like in the last demo, we were creating a model, so you can load that same model from the file system and then do predictions on the stream data. So you basically have real-time processing there. So the way it looks like this, so you can ingest the data, you can stream it. So in Kafka, you can stream it in multiple topics. One that can be consumed by your machine learning service and basically build models, train the classifiers, and save new models that you can then reuse in the streaming when you stream normalized data, basically. So here, the two streaming parts here is it's all Kafka. The Spark takes care of the machine learning. All this is running on Mesos, basically one system. Yeah. So what's next? Yeah, this architecture has showed us to be very flexible. It's also a stable platform that can actually scale. I don't know endlessly, but it seems like it. And we're really early in this stage of building out this platform, but it has proven to be really good for productivity for the company. So it's a good choice, and we feel happy about it. Yeah, Spark is a very powerful tool. So if you haven't looked at it yet, I would recommend taking a look at it because it's very capable of a lot of things. So that's it for my presentation. So if you have any questions. So the library dependencies, basically, if you create a Docker image that has those dependencies, you can just use that when you deploy. So it hasn't really been an issue. Is that what you mean? Just have to make sure it's there?
It's just basically the library that they included has so much dependency, and it's platform specific. The Fortran library, they require some Fortran library that requires special binary Linux and Mac OS X and videos. Those are all kind of defeat for the purpose of the portability.
Yeah, but with a Dockerized environment where you can actually specify those dependencies. But yeah, it's the G-Fortran dependency. Yeah. If there are no more questions, I think that's it. Well, there's one more.
Yeah, can you talk about some of the results
How to actually store the data, or? Yeah, so you probably most likely store them using HDFS. Yeah, HDFS, we use Cassandra as well. So, but HDFS is a really common one. Yes, yes. Yeah, both HDFS and Cassandra are good options. Okay, thanks.